Hi folks, this is the last video in the forces unit, and the title is Calculating the Values of Individual Forces. The essential question is, how do we use free body diagrams and what we know about sigma force to figure out the values of individual forces acting on an object? So these two things that we've learned how to do so far, draw free body diagrams and calculate sigma f using the sigma f changing momentum equation, work together to give us a lot of information about the individual forces acting on an object. The strategy for solving these problems is as follows. The first thing you should always do when you know you have a problem with an object in changing momentum is draw a free body diagram and put as much information as possible in your labels. So the direction, show the size of the forces relative to each other with how long your arrows are, the type of force, and the object causing that force. The second thing is to think about whether those forces are balanced or unbalanced. So think about what you know about the motion of the object. Is it speeding up in a direction or slowing down in direction, or is it moving at a constant velocity? And those things are going to tell you whether your forces are balanced or unbalanced in each direction. By that I mean up and down versus left and right. Then you'll use the changing momentum equation, sigma f delta t equals m delta v, to solve for any missing values. Don't forget that when you look at your free body diagram, sigma f is just the leftover portion of the forces, not any of the forces on their own. So let's go through a couple challenging example problems. A sled is being pulled at a constant velocity to the right. You're also told that the force of gravity acting on the sled is negative 450 newtons because it's down, and the rope is under 125 newtons of tension force. Find the values of all the forces. So as I said, the first thing you should do is start with drawing your free body diagram. I just put the information in that problem up on the top right so you can see it again. So that box represents my sled. I'm going to go ahead and put in all the forces I know and all the information that I can. Start with Fg. It's a gravitational force. We know it's downwards, and the object that causes it is Earth. Then I'm going to put in a normal force upwards from the ground, and I'm going to indicate that I know those two forces are equal to each other because it's balanced, because the sled is not speeding up or slowing down up and down. Then I'm going to put in force of tension from the rope, and that's going to be to the right, so we're pulling that sled to the right. And I'm going to put in a force of friction, which is slowing the sled down, and that's from the snow. I know the tension force and the friction force have to be equal to each other as well, because that sled is being pulled at a constant velocity. So delta P is 0. It's not changing momentum at all as it moves, which is a little bit challenging, because people tend to think if the sled is moving to the right, we must have a big Ft to the right. But if it's moving at a constant velocity, it's actually the same as the friction force acting on that. Then I'm going to start filling in the values that I know. The problem told me that the force of gravity was negative 450 newtons. But since I've already identified that that has to be the same as the normal force, I can also say that the normal force from the ground is also 450 newtons. Again, the problem tells me that the person's pulling with 125 newtons of force on that rope, which means in this case the force of friction from the snow is also negative 125 newtons, because it has to be balanced with the force from the rope. Another example problem. A 6-kilogram bucket is being lifted up a well with a rope. It starts at rest and speeds up to a velocity of 5 meters per second in 10 seconds. Negative 60 newtons of gravity force are acting on the bucket. How much tension force is acting on the rope? All right, so let's work on solving this bucket up a well problem. Again, the first thing I would do is draw my free body diagram. This time I put everything I know in there right from the start. I put my gravitational force from Earth in, and I even put the value because it tells me it in the problem, negative 60 newtons downwards. And I drew a tension force from the rope. You'll notice that this time I did make that tension force longer than the gravitational force, and the reason is because this bucket is speeding upwards. So we have to have an unbalanced force. We have to have some extra sigma f in the upward direction so that we can speed up in the upward direction. And that's the goal, is to figure out what that Ft is. I know it's got to be bigger than 60, but I don't know what it is. The next thing I'd probably do in this problem is make a no-want list like we've done in previous units. So I know that the mass is 6 kilograms, delta T is 10 seconds, and delta V is positive 5 meters per second. And what I really would like to know is sigma F, because if I know how much unbalanced force there is, then all of a sudden I can figure out what that Ft value is as well. I'm going to go into my changing momentum equation. Sigma F delta T equals m delta V, and I know 3 of those values. The only thing I don't know is sigma F. So I plug in sigma F times 10 seconds equals 6 kilograms times 5 meters per second. When you solve for sigma F, you get positive 3 newtons. So the unbalanced portion of the forces is 3 newtons. That's how much leftover force there has to be, 3 extra newtons upwards to cause this bucket to speed up. So Ft has to be 3 newtons bigger than Fg. And what's 3 bigger than 60, which is positive 63. So the tension force in the rope has to be 63 newtons. That's what would allow me to have a sigma F of 3 newtons. So to summarize, how can we use free body diagrams and sigma force together to figure out the values of individual forces acting on an object? It's not always the same path, right? We need to work from both ends. We sometimes are using our sigma force equation first. Sometimes we're working from our free body diagram first, but those two things work together to figure out the values of all the individual forces that you might want to know. Thanks for listening.